equilibrium concentrations. All right, so let's use Henderson-Hasselbalch and design a buffer system if we want a pH of 4.6. And a good rule to remember is that a buffering solution is most effective when it's plus or minus 1 away from the pKa. So that's a good thing to keep in mind for research as well. If you're really far away from the pKa, it's not going to be a good buffering system. And this is a mistake that people make in the lab sometimes. So you may run into that in some of your laboratory courses. So we want a buffer about pH 4.6. So we can look at our ionization constants of acid. And of course, we're always doing everything at room temperature in this unit. And so we can look at what pKa's are of some weak acids. And acetate. Acetate is easy buffer to get your hands on. Acetate is quite available. And it has a good pKa, 4.75. So that's great. We can use that in designing our buffer. So acetic acid has the right pKa, and we're all set. We can prepare our buffer. But we'll need to add the acid and the conjugate, and we need to know how much acid and how much of the conjugate to add. So we can use Henderson-Hasselbalch equation for this. We're creating a buffer, and so this is an equation we can use for buffers. We know what pH we want. We know the pKa of the thing we're going to use, and we want to figure out how much of the acid to use and how much of the conjugate to use. We need to know the ratio of one to the other to set up our buffer ideally. So we can plug our numbers in and calculate that. So we can rearrange this if you want so that the unknown is on one side and we have the pKa and the pH on the other side. And so we have here our pKa minus our pH, and we get 0.15. Now we need to do inverse log and come up with the ratio. And the ratio that we want is 1.4. So we want to have a ratio from our acid to the conjugate of 1.4. Well, how much exactly are we going to add then? We know the ratio now. How much are we going to add? Well, you could use 1.4 molar and 1 molar, for example. That would have the correct ratio. But how do you know if that's going to be good? Well, the ratio is more important than the exact amounts. However, the amounts get to this issue of sort of the capacity of the buffer, how resistant it is to changes in the pH. So if you use too low concentrations of both, it won't be all that resistant. So you need to have, if you need to have a better buffering capacity, the higher concentrations that you should use. And you can use Henderson-Hasselbalch then to calculate what's sort of the minimum amount you use, the minimum amount to have that 5% rule work. So in the example I told you about this, this condition, the buffer in the blood was pretty good, but the acid was so much that it overwhelmed the buffering capacity. So if there had been larger concentrations of the buffer, that would have certainly helped in that case. So the higher the concentrations you use, the more resistant to change. And that's the idea of buffering capacity. So, and if you use too low concentrations, then your Henderson-Hasselbalch equation won't even be valid. So we can go back and calculate what is sort of the minimum concentrations we need to use for Henderson-Hasselbalch to be valid to meet that 5% rule. So for a pH of 4.6, hydronium ion concentration is 2.5 times 10 to the minus 5. And so then if we work our equation backwards, we want to be less than 5%. So we have this over the concentration of either one of those times 100% gives you 5%. So the concentrations need to be greater than 5 times 10 to the minus 4 moles, or you won't meet this 5% rule. So at least to be greater than that, and they need to be in the right ratio. Other than that, you're somewhat free to decide what you're going to do with that. And there may be other considerations involved. If you're working with a certain concentration of protein, you might not want your buffer concentration to be too high. It might start interfering with the enzyme assay, for example. And often buffers are somewhere around 100 millimolar. That's pretty common concentration for buffers.